In this, we are going to learn about the logarithmic function. In the previous lecture, we talked about what we call the exponential function, which is given as y equal ax. And we also assume that a is positive and a are not equal to 1. So that is the exponential function, and why we have the condition a not equal to 1, because there are situations like 1 squared equal 1 cube, and these kind of situations can create problems later. So we can avoid the situation, so we assume that a not equal to 1. So this is what we call the exponential function. And then we also talk about the graph of these two functions. So we have a graph when a greater than 1, and then we have a graph for a in between 0 and 1. So we have these two. When a greater than 1, we get an increasing function. So it passes through 1 and increases. So this is and also in that it's always passed through 1. So this is an increasing function when a greater than 1. So this is y equal x when a greater than 1 as an increasing function. And then y equal 0 is a horizontal asymptote. If a is in between 0 and 1, we get a decreasing function like this. So it is going down and it can pass through 1, and then y equal x is the asymptote. So this one also passes through 1. So that's a decreasing function now. So it's again y equal x. But a is in between 0 and 1, so it's like a fraction. So when you can see that a is a fraction, what happens when x increases is getting smaller and smaller, because it's like, for example, like 1/2. If you look at 1/2 squared, which is 1/4, and if you look at 1/2 cube, which is 1/8, so you can see it decreases. That's why. So when x increases, the function decreases. And then we also know that increasing and decreasing functions are 1-to-1. So we notice that increasing or decreasing, one of them, increasing or decreasing functions are 1-to-1. So since it's 1-to-1, then we can define the inverse. So the inverse exists. So so you can say, since both functions, I think both cases actually, both functions, that means for a greater than 1 and a between 0 and 1. Since both functions are 1-to-1, the inverse is defined. Inverse exists. Inverse exists. Inverse exists. So the inverse is there. So what we can do, we're gonna find the inverse, and we remember how to find the inverse. So we can see that. So if we have y equal ax, to find the inverse, what we are gonna do is we switch the variables. So we can write this one as x equal ay, and then you can see that then y is defined as a implicit function. It's not explicit, but y is defined as an explicit function now. So the goal is to find the y. So to do that, we're going to define this new function called the logarithmic function. So so the y is the new function. So this y is the inverse, and which is a new function, and then we define this new function y as a as the logarithmic function. So that means if this is the case, then we define this simply as y equal logarithm of base a. So that's the base. So you can see a, so that's the base. So base a, and then we write x there. So that is how we define the logarithm. So that is simply the inverse function of the exponential function. So we can write the definition now. So the definition is, we can say, for a positive and not equal 1, so we can write uh, we can say, so y equal log ax if and only if x equal ay. So whenever you have x equal a to the y, we write this as y equal log ax. So that is the definition. So this is the definition of the logarithm. And the assumption is a, we assume that a is not equal to 1 and a is positive. Good. So that means again we have two cases for a greater than 1 and a is in between 0 and 1. So that means you will notice that the log is simply the index. So log is simply the index. When you write a number using a base a, the index is the logarithm. So that's gonna helpful if you remember that. So uh, log ax is the index when written as a to the y. So if you written as a power, the power is the logarithm. Okay, so let's look at the graph of these two functions in the two cases. Before we look at the graphs, let's look at two situations. For example, we know that 2 to the 3 equal 8. So that means in the log form, you can write this one as log base 2 to the 8 equal 3. So the reason is when you write 2 using the when you write 8 using the base 2, and you're gonna get 3 as the power. That's what it means. And also you can see that for example um, 2 to the negative 3 2 to the negative 3 is 1 over 8. So you can write this one as so you can say log base 2 1 over 8 equal negative 3. So you can see it's just a log form, but you write in a different way. So it's simply log means the index. So now look at the two graphs. So let's look at the situation when a greater than 1. So we know that we can first look at the exponential function. So the exponential function is for a positives, the exponential increasing function. So we have this and then actually before that I'm gonna draw the line y equal x, because we know that we learned this before. If you reflect across the y equal x line, what you get is the inverse. So so that means for first look at the uh, so we draw the y equal x line, and then we look at the exponential function. So the exponential function is like this. It's going to go and increases. So it's going to pass through 1. So that is y equal ax. So this is y equal ax. Now what we can do, we're going to reflect this curve about the y equal x line. So we're going to get this one. So this is the graph of the logarithm function. If you look at the mirror image or reflection about the y equal x line, what you get is the inverse. So in this case, the logarithmic function. So if you look at the uh, mirror image of that, so what you get is this. So so what happened here is the so the horizontal asymptote now become a vertical asymptote. So the x equals 0 is a vertical asymptote now. Earlier it was the horizontal asymptote y equals 0. Now say it is the vertical asymptote x equals 0. So the new graph is now this is y, which is the logarithm now. So it's a logarithm of ax. So that is for a greater than 1. So and then similarly we have for a in between 0 and 1, and then we know the graph in this case. So we have the exponential graph. Again we draw the line y equal x line, because we can look at the mirror image of that. So that means, so we know the graph at this time is a decreasing function. So it's gonna go like that, uh, and again it's passed through 1 again. So what you're gonna do is we look at the mirror image of that. So that means this point is sitting. So you can see this point sitting on the line. So that means that stays there, and then one jump to the other side. So that means the so new graph gonna look like this now. So it passes through. So it's gonna be the horizontal vertical asymptote and pass through this point and go like that. So that is the graph of the log function for a between 0 and 1. So this is the y equal ax graph for a between 0 and 1, and this is the graph y equal log ax when a is between 0 and 1, and the point this is the point 1. And again, x equals 0 is a vertical asymptote to the new graph, y equals 0 is a horizontal addition to the old graph. Good. So so there are some properties that you can see. So let's look at the domain and range first. So you can see so the domain of the old function was so the domain is negative infinity to positive infinity, and the range of the old function was 0 to infinity. And then when you take the inverse, they're going to switch each other. So that means the new domain is, you can see it is from 0 to infinity. New range is going from negative infinity to positive infinity. So they switch each other. The same thing happens here, and then you can see so the domain of the original function is negative infinity to infinity, and the range is from 0 to infinity. And then the new function, you can see the range. So the domain is only from 0 to infinity, which is the range of the previous function, and the range is going from negative infinity to positive infinity, which was the domain of the previous function. We switch the domain and range. Okay, so there are some other properties you can see, and then so one is increasing, one is decreasing. So one property is for a greater than 1, so y equal log ax increases, and for a between 0 and 1, y equal log ax decreases. So and then also we can see that the passes through uh, the point 1 0, both graphs. So those are the major properties that we see. And then also we have x equals 0 is a vertical asymptote. Okay, so those are the major properties of the logarithmic graph. So let's try to look at other special bases. So we talk about the general base A, but there are two special bases. So let's talk about that. So the first one is what we call the natural base. The second one actually, so is the natural base E, and then we talk about E is a number which is close to say 2.718. That's what we normally call natural base. So under the natural base, we can write the log in a different way, and so also this is actually less than 3, so that's sometimes helpful. So what happened? So we can write this. The new definition is we can say if x equal so you can say e to the y, then we can write this one as the natural log. So we can call this natural log, and we write this special notation. So we can write this one as y equal natural log. We write ln x. So we do not write the base in this case. So what this means is, so ln x means log ex. but we do not write e, so we just write ln x. So that's a special situation when we have the base e. And then also there's another base, what we call the log base. So that's a third one. So we have the general base a. Now we have this base e, what we call the natural log. So we read this one as a natural log. So we call this natural log. Please note that we write the letters in a reverse order. So we call this natural logarithm. Okay, natural log. And then the base 10. So we have the base 10. Base 10. So when you have base 10, so that means x equal 10 to the y. We can write this one as even without 10, we just write this one as log x. So we need to just write log x, that means the base 10. But if you are in computer science, sometimes they just write log for base 2 because the base 2 is more important for them. So you have to be careful whether they mean by log what they mean. They mean whether base 10 or base 2. And if you use a calculator use base 10 for log. So what we use here is, so when you write just log log x, that means log 10x. So we ignore 10. When we write log e, we write that one as natural log. So we write a different notation. So we use ln for that. This is and when we write log is the base 10. Okay, so let's write a small note. So in computer science, log x sometimes means log 2x, the base 10, base 2, base 2. Okay, so those are the three bases that we talk about: the general base, and then the base e, and then also base 10. So let's look at a few examples. So as the first example, let's try to do this one. Let's say convert to exponential form. So as the first example, so let's look at what is log some number like base a 4 equal 5, something like that. And just if you look at the definition, so by the definition of log, this means that, and you notice the base, that's the base a, and this is the index 5. So that means you can write this one as a to the 5th power equal the number 4. So that's what it means. And then the second example, let's say log e, let's say b equal -3. So you can write this one as here the base is e, so it's e -3 equal b. And then let's do this one. Let's say log 5 equal c. So if you just write log, that means base is 10. So it is 10 to the 6th power equal 5. So let's do another one. So let's say log 2 equal x. So if you see log 2 equal if you say ln2, when you say ln, that means the base is e, that means e to the x equal 2. So we just write the use the definition. So what's the definition? Whenever you see x equal ey, that means y equal e to the so we can write y, so y equal the log, actually let's not write e, so let's write like a, like a general a. So let's say x equal a to the y, that means y equal a x. So this is how we write it. So y is the power, it's just the power. Okay, so now let's do the other way. So let's try to convert to the log form. So convert to the log form. So the first one, so let's say you have a number like 1.5 to the some power like 3 equal m or something. So then what does that mean? So you can see this is the base. So it's just a number. So that means you can write this one as log 1.5 base the number m equal 3, because the 3 is the index, so that's the log. And then b, so let's say e to the c equal 8. So that's like a special base e, so we use the natural log. So that means the natural log the number 8 equals c. And then we can write a number like this. So let's say 10 to the negative 3 equal 0.001. So that means if you use the log notation, this means that it's a base 10, that means the log. So we can write log 0.001 equal negative 3. Okay, so that's how you convert between the log and the exponential form. Good. So let's look at a few special cases also. So let's look at this problem. Find the exact value of, let's do these 4. So the first one is log 2 to the 16, then b log 3 to the 1 over 27, c log e to the negative 4, and the d log a to the 1. So what you're trying to do is you try to write the number using the given base, and then whatever the index you get is the logarithm. So the answer, so you can say the first one, since you can say 16 equal 2 to the 4th power, logarithm of 2 the number 16 is 4, because logarithm is the index. And then b, again I can say since so you can write as 1 over 27, which is 1 over 3 cube, which is 3 to the negative 3, logarithm of base 3 1 over 27 is the index, which is negative 3. And c, so this is actually clearly says what it is. Let me change this problem a little bit. So I'm going to change this to ln. So let's call this is ln. So it's like more interesting. So what we can see is, since you can write e to the negative 4 as just one number, this is simply e to the negative 4. So because of that, you can write this number using the base e. So that means you can write this one as so this is natural log e to the negative 4 is simply negative 4, because it's already written using the base e. And the d, so this is also very interesting. So you can see that since 1 is a to the 0th power for any base a not equal to 0, so you can see that the log to the base a1 is 0 always, so it's going to be 0. So that's a special case. Okay, so that's how you do those 4 problems. So let's look at some of the domain problems now. So let's try to find a few domains. So as a problem, let's try to do this. So so find the domain of find the domain of so the first one is fx equal log base 2 x plus 3, just some numbers, and the second one gx equal log 1/2 base to the 1 plus x over 1 minus x, some fraction, and then c, let's say hx equal log to the base 5 absolute value x minus 4. So only condition that we need to know is when you have y equal log any base x, so we know that the domain is simply a 0 to infinity for both cases. For a, whether a is greater than 1 or a is in between 0 and 1, you have the exact same domain. So we can use that fact here. So using that fact, then we can solve this very easily. So we can say since the domain, so we can write this, since the domain of a since the domain of a logarithmic function is 0 to infinity, then we can say the first one, what should happen is, since the domain is 0 to infinity, whatever the value you plug in has to be greater than 0. So we just write the condition. So we need simply x plus 3 greater than 0. So that means if you solve this one, this says that x is greater than -3. So that means the domain of the first function is, if you use the set builder notation, it is x such that x greater than 3. Or if you use the interval notation, you can write this one as actually it's -3, yeah, not 3. So -3. So if you use the interval notation, you can see it is -3 to infinity. So you can use one of those forms. Okay, so let's look at the second example. And in the second example, you can see that the base doesn't really matter. So what we need is the function, the x part has to be greater than 0. So that's the only condition we need. So that means for the second one, so we can also, so we need 1 plus x over 1 minus x greater than 0. So whatever the number you plug in has to be greater than 0. So this is simply an inequality problem, and we have solved several inequality problems earlier. So when you want to solve an inequality problem, what we need is zeros from the numerator and the denominator. So we have zeros. We can see from the numerator it is -1, from the denominator is 1. So what we're going to do, we're going to put them on number line and then pick test points. So we're going to put them in the order, so it's -1 to 1, and then we pick test points. So we pick a test point 2 on this side. So if you plug in 2 to the top and bottom, so you get from the top you get plus, from the bottom you get minus. So plus minus means minus, and then we put t equals 0 here. We put t equals 0, you get 1 over 1, so that means positive, so which is positive. And then you're going to plug in t equals -2. If you plug in -2, top is negative, bottom is positive, so it's negative. So that means you can see only in the middle it is negative, it is positive. That's what we are looking for, but you still have to remove the zeros from the denominator. That means we can remove 1. So so that means the answer would be anything in between -1 and 1. Good. So you can say the domain is -1 to 1. Good. The last one. So you have the absolute value function. So it's a log absolute value. So what's really happened here? So we can see when you have log the a absolute x, so we can consider both positive and negative values, because when you look at just the positive x, so that's what gonna happen. So you have everything on the positive side pass through 1, but when you have the absolute value, that means you can consider both positive and negative. So it's gonna be like that now, and then this is -1. Only thing that you do not have is the value 0. So that means if you look at the third problem, so what you need is simply x minus 4 not equal to 0. In other words, you can see x not equal to 4. So that means the domain of the last function is simply everything except 4. That means -infinity to 4 open, 4 to positive infinity. So because it is the absolute value function. Okay. So next, look at several graphs and inverse of several logarithmic functions. So let's do this problem. So let's say graph the function and find its inverse. Let's do both. So let's look at the first one. Let's say fx equal negative ln x minus 2, and then you can see that for this problem simply the domain is any x such that uh, x minus 2 greater than 0. So in that case you can see x greater than 2. So that's the domain, and then we can graph this step by step. Again, we can start with the natural log and a shift and then the negation. So we can go with y equal ln x, and then y equal ln x minus 2, and then y equal negative ln x minus 2. So if you go with y equal ln, that we know that's just the basic log graph. So it's gonna go like that and pass through 1 for because the here base is e, so which is greater than 1. So we have this kind of graph here with the x equals 0 is the vertical asymptote. Now in the next one we're gonna shift the graph 2 units. So shift the graph 2 units, that means the horizontal vertical asymptote now moves. So it's gonna move 2 units. So that's the y equal 2 line, and then also the intercept moves to 3 now. So that means the new graph is going like that. So so this is the number 2 and this is number 3 and this is 0. So that's the y-axis and that's the x-axis, and then we have the negation. So you're gonna negate, you're gonna reflect across the x-axis. So that means the new graph is still the line y equal the x equal 2 is still there. So what happened, so graph reflect, so that means the asymptote gonna go like that and then go like this. So that is the new graph. So it is 2 negative 3, this is 0, that's the y-axis and that is the x-axis. So this is a new graph. So so y equal negative ln x minus 3, and you can see that the so the domain is from see, so we can write this again. So it is from 2 to infinity, and you can see the range is going from all the infinities, negative infinity to positive infinity. That's the range. Okay, so that is the graph of the negative ln x minus 2. Let's also try to find the inverse of this function. So we can follow the 4 steps that we discussed. So find the inverse, find the inverse. So we're gonna follow the 4 steps. So we have fx equal negative ln x minus 2. So the first step is you replace fx by y, so it is negative ln x minus 2, and then the next step is you switch the 2 variables, so it is ln y minus 2. So the goal is to isolate the y term. So the best thing that we can do is we can write this equation in the exponential form. So if you write this in the exponential form, you can write this one as, so that here we first gonna so I'm gonna write this one. So write in exponential form, exponential form. So so for that, first we're gonna multiply by negative to isolate the log term. Now we know that the base is e here, so we can write this one as e to the negative x equal y minus 2, and then we can add 2, so you're gonna get the y. So it is if you add 2, so you can see that it is e to the negative x plus 2 equal y. So if you switch, you can write this one as y equal 2 plus e to the negative x, and then finally we replace this y by f inverse, so we can say f inverse x equal 2 plus e to the negative x. So that is the inverse function. And then we can see that the domain of this function is, so what is the shape of this graph now? So if you graph this, and this is a very simple graph. So what happened, we know that e to the negative x was a shape, but you can see it's going to lift by 2. That means there's asymptote. Now it's going to pass through y equal 2 line. So so the basic graph is now that's the e to the negative x, that's we know have a shape like that, and then it's gonna get the asymptote. So so this number is, so this is the number 2, so that means one more, that means this number 3. So that is the graph of the function. So it is y equal 2 plus e to the negative x. So that's the graph of this function. Good. And then if you draw both graph in the same one, so what's going to happen, you can see what kind of graph we get. So there was the y equal to vertical asymptote, and then so the other graph, the log graph, was going like this. So that was the graph we got for the log function, and you can see this is simply the reflection about the y equal x-axis. Good. So let's do one more graph problem. So we have fx equal 3 log x plus 1 minus 2, and you can see that here is a log, that means the base 10. So the base is 10. So first we can graph this function using step-by-step approach. So we're gonna go with y equal log x, and then we can do y equal log x plus 1, and then y equal 3 log x plus 1, and then finally we have y equal 3 log x plus 1 minus 2. So let's do one by one. So the first one is just the basic log function, so which has the asymptote y equal the y-axis asymptote, so it's going to pass through 1. So it's gonna get that. So that is the first one, and then the next one is we're gonna move this one to the left by 1. So the next graph is, so it's gonna move the asymptote. So the asymptote move 1 unit. So the new graph is which now go through 0 and get the asymptote. So this is passing through 0 now. and in the next one what we can do, we're gonna multiply by 3, so it's gonna 3 step, like it's gonna like a more steeper this time. So the graph gonna be uh, like more steeper, so it's 3 times more steeper. It's gonna be like that here, and then like this. So that's the graph of the third one. So we have this. So this is a more steeper graph, 3 times more steep. Uh, so it's pretty much looks the same. It's more steep. Okay, and then finally what we can do, we're gonna bring the graph down by 2 units. So it's gonna go the intercept gonna go 2 units down. So finally we get this graph. So this is the asymptote, no change. So the point gonna move 2 units down. So that means the new graph gonna look like this. It's passed through that, and the same asymptote. So that's the graph of the final one. So this is the x-axis and the y-axis, and this is the x equal -1 line. So that's the graph of the new log function. And then also we can find the inverse using the 4-step method. So we start with fx equal, we have 3 log x plus 1 minus 2. So the first step is we replace fx by y. So we have 3 log x plus 1 minus 2. So then we're going to switch the 2 variables. So we can write this one as x equal 3 log y plus 1 minus 2. So the goal is to isolate y term. So to do that, first we move the -2 to the other side and divide by 3. So that means we can write this one as x plus 2 divided by 3 equal log y plus 1. Log means the base 10, so that means we can write this one as y plus 1 equal 10 to the power x plus 2 over 3, just using the log definition. And then y is simply subtract a 1 from this, so it is x plus 2 over 3 minus 1, and then we can replace this one as f inverse x. So f inverse x is 10 to the power x plus 2 over 3 minus 1. So that is the inverse function. Okay, so let's try to solve several logarithmic equations now. Solving a logarithmic equation. So what's a logarithmic equation? As you can see, an equation that contains logarithm equation that contains logarithms are called a logarithmic equation. So the one of the basic idea that we're gonna do is, if you have a logarithmic equation, we're gonna convert this into the exponential equation. That's sometimes the kind of basic idea. So that means if we have a logarithm a to x equal y, we can write the exponential equation. So that means we can simply write this one as x equal ay. So that is a kind of way to do that, and then we're going to follow the steps that we use when you solve exponential equations, such as equating. So after that, what we're going to do, we have things like this. We know that if we have AV equal AU, this implies that V equal U. So things like that. So we're going to do these kind of things, and then solve the equation. So what we do, we can transform the logarithmic equation into an exponential equation, and then use the methods that we use for solving exponential equations. So let's look at several examples. So solve A log 3 to the 4x minus 7 equal 2 and B log x 8 equal 2. So let's look at the first one. So what we can do, as we discussed, we can transform this into the exponential form. So we have log 3 4x minus 7 equal 2. We can write the exponential form. What's the exponential form? That means 4x minus 7 equal 3 to 2. And then we know that 3 squared means 9. So we have 4x minus 7 equal 9. So that means 4x equal 7 plus 9, which is 16. And then this is that x equals 16 over 4, which is 4. So x equals 4. So it's a simple calculation. And let's look at the next one. So we have b log x to the 8 equal to. Again, we can write the exponential form. So this means that x to the 2 equal 8. So that means what we need to do is take the square root. So once you take the square root, don't forget that there are two answers. So that means x equal plus or minus square root 8, which is plus or minus, because we know that 8 equal 4 times 2. That means 2 square root 2. Okay, but we know that x is the base. X is the base, so that means x has to be positive. Since x needs to be positive, so you can say since x is positive, x equal to square root 2. So that's how you solve for x. And then we can also solve one additional problem that was not given as a problem. So let's say we have like extra problem log 3 to the 9 equal x minus 1, something like that. So again, we're going to convert this into the exponential form. So we can write this one as 3 to the x minus 1 equal 9. 9 we can write using the exact same base. So that means we can write this one as 3 squared. It has to be the same base, because if the bases are the same, then the exponent has to be the same. So this implies that since the two numbers are the same and the bases are the same, then the exponents has to be the same. So you equate the exponent, and then this says that if you add 1 plus 2, which is 3, so x equal 3, and that's the only value we get. So let's also solve one by some exponential equations. So let's say the next one is, this is solve. So the first one is e to the 3x equal 5, and b let's say 3 equal 4 minus e to the negative 2 t minus 1. So you're going to get questions like that in later. So let's try to solve these two. So let's look at the first one. So which is e to the 3x equal 5. So if you get a exponential equation, what we can do is we can write this one using the log form. So we go to the log form. So the log form is, you can write this one as 3x. So you can say 3x, that's the index, which is the ln 5. And then what we can do is we can divide by 3. So when you divide by 3, so you get x equal ln 5 over 3. So that is the exact value. And if you have a calculator, you can find the approximate value for this one. So let's look at the second problem, which is so 3 equal 4 minus e to the negative 2 t minus 1. So again, what we can do, we can isolate the exponential term first. So to do that, what we can do, we can subtract 4 from both sides. If you subtract 4 from both sides, you can see that negative 1 equal negative e negative 2 t minus 1 t minus 1 and then we can multiply by negative sign, multiply by negative 1 or divide by negative 1, then you're going to get 1 equal e to the negative 2 t minus 1. So this means that because this is 1 means, so you can write the log form. So if you write the log form, you're gonna see that the index, that means negative 2 t minus 1 t minus 1, that's index, equal, in this case the this is e, so that means ln1, and then we in a problem we know that ln1 is 0 because 1 is to any power, it's 0, so because of that ln1 is 0. So that means so you can see that you can divide by negative 2, so it's t minus 1 equals 0 over negative 2, which is still 0. That means t is simply 1, so t equal 1 for this problem. So this is the end of the logarithmic discussion, and then in a different video we're going to solve several complicated exponential and logarithmic equations.